In this video, I want to give an introduction to eigenvectors and eigenvalues. So I want to begin with an example to help motivate what these things are. So let's let A be this matrix, 1, 4, 3, -3, and let U and V be these two vectors. So what I want to do is I want to look at what happens if I multiply A by the vector U, and if I multiply A by the vector V. Let's see what we get out. Okay, so when we multiply A by U, what we will get if we do the row column rule, for example, I'll get 1 times -1 plus 4 times 0, and that's -1. And then I'll get 3 times -1 plus -3 times 0, so that's -3. Okay, and then if I multiply A times V, this one, let me do it a little bit more quickly. So I'll get 1 times 2, which is 2, plus 4 times 1, which is 4. That adds up to 6. And then in the second entry, if I work out the multiplication, I'll get 3. Okay, so the thing that I want to notice about 6, 3 is that notice that this is a multiple of this vector v that I started with, 2, 1. It's 3 times that vector. So the vector 6, 3 that I outputted is 3 times the vector v that I inputted. But notice that that type of thing didn't happen with u. Like the output that I got here was not a multiple of u. This was not a multiple of u. So this vector v is special in a sense. So let's draw a picture of these inputs and outputs on an xy plane to get a feel for what they look like. So the vector u was -1 in the x direction and 0 in the y direction. So that looks like this. That's the vector u. And then if I draw the output that I got by multiplying a by the vector u, so we get -1, -3. So that looks like this. So this is a times u. And now let's draw v and then a times v. So v is 2, 1. So 2, 1. Sorry, I think I'm missing a tick mark here. Sorry, yeah. 1, 2, 3, 4, 5. Yeah, I meant for these big tick marks to be every 5 units. So this is 5 units. This is 5 units. And I think I was missing a tick mark there on my y-axis. Okay, so the vector v is 2 in the x direction, 1 in the y direction. So that looks something like this. And then a times v was 6, 3. And we know that that is going to be 3 times v, so it's 3 times as long. And there's the vector av. In fact, let me go ahead and backtrack and label my first vector v. So the vector v I'd forgotten to label. V was this green one. Let me just draw it one more time so I can see a little bit more clearly. There's v. Okay, so there's something special about the vector v here. V is special in some sense because multiplying by my matrix A scaled it. It kept it in the same direction, but it just scaled it by a multiple. Okay. So at this point, we're ready to introduce this term that's called an eigenvector. Okay, so we're ready for a definition. Okay, so here's the definition. Let me scroll down a little bit more. Let A be an oh, and I see another fix that I want to make. Let A be an n by n matrix. So it's got to be a square matrix. An eigenvector of A is a vector x such that, and I need two things to be true. The first property is that A times x has to equal, so this symbol is called lambda. So the symbol in front of the x is a Greek letter. This is the Greek letter. Lambda. Okay, so the first property is that A times x has to be equal to lambda times x, where lambda is some real number. It is some scalar. So what this is saying is A times x is going to be some multiple of x. And the second property is that an eigenvector x cannot be 0. It is not allowed to be the 0 vector. Okay, and when this happens, the number lambda is called an eigenvalue. So x is called the eigenvector, lambda is called the eigenvalue. So in the context of the example that we were looking at up here, we noticed that A times the vector V ended up equaling 3 times V. It scaled it by a factor of 3. So this vector V is an eigenvector. It is an eigenvector. So here I saw V as well. So V is an eigenvector. Multiplying V by my matrix scaled it. So it's an eigenvector. And then the eigenvalue is this scaling factor. So the number 3, that's my lambda. That's my eigenvalue. This is an eigenvalue. And I forgot to just mention that I abbreviated eigenvector here. I just wrote eigvec. That's just my abbreviation for eigenvector. Okay, on the other hand, notice that the vector u, the other vector that we have in this picture, is not, this is not an eigenvector. And what makes it not an eigenvector is since when we looked at A times u, when I multiplied u by A, this is not a multiple. This was not a multiple of the vector u. So that's what makes u not an eigenvector. So a lot of what we're going to be doing in this chapter is using this concept of an eigenvector, an eigenvalue, to express a matrix in a special way that makes computations easier. And this is just the introduction to that. Okay, so next I want to observe something about eigenvectors. Okay, so notice that in the example that we just did, we saw that when we took the matrix A and we multiplied it by the vector V, what we got out was 3 times V. Okay, so and we said that V, this vector V, was an eigenvector. So what I want to do now is I want to multiply both sides of this equation by just some arbitrary scalar, C. So let's say I do C times the left-hand side, A times V, and then I do the same thing to the right-hand side, which is C times, and the right-hand side was 3 times V. So I'm just multiplying both sides by 3. Sorry, by C, where C is a real number. Okay, so now what I'll do on the left is I can move this scalar inside of this matrix multiplication and write it as A times C times V. So I can do that by the linearity property of multiplying by a matrix. And then I can also move the scalar C on the inside of the right-hand side in front, past the 3, and get 3 times C times V. Okay, so notice what we have here. We have A times this vector, C times V, equals this number, 3, times that same vector, CV. So because we have this same vector over here, we might notice that, oh, this is an eigenvector. This isn't, let me connect that arrow there. This is an eigenvector. C times V is an eigenvector as well. Because it sort of satisfies this property that I need, where A times the vector equals a number, lambda, times that vector. So C times V is sort of being written in this spot of this vector x. And this is going to be true as long as, so this is an eigenvector, if, as long as the C doesn't equal 0. Because remember, if C equals 0, then the vector C times V would be 0, and 0 is not allowed to be an eigenvector. Okay, so the key takeaway from this is that if V is an eigenvector of a matrix with corresponding eigenvalue, lambda, so this is just my abbreviation for eigenvalue. Sometimes I'll just write eig, and then this apostrophe, and then val. So if V is an eigenvector with corresponding eigenvalue, lambda, what we just observed is that C times V is also going to be an eigenvector of A, corresponding to the same eigenvalue, lambda. And that's going to be the case for all values of C except for 0. Because if it were 0, so the reason for this is, if C was 0, then the vector C times V would be 0 times V, which is 0. And 0 is not allowed to be an eigenvector. Is not allowed to be an eigenvector. So you might be wondering, wait, why is 0 not allowed to be an eigenvector? And there's actually a pretty quick reason for that, but I'm going to leave that as a homework exercise because I think it's a really interesting problem. So in the homework, we'll look at, wait, why is 0 not allowed to be an eigenvector? Okay, so let's do another example. Okay, so here's our next example. So let's let A be this matrix. So this is the same matrix that we've been working with, but this time I want to show that -5 is an eigenvalue of A, and then find its corresponding eigenvectors. So we've already seen that I think 3 was an eigenvalue in the previous example that we just looked at. Now we're going to show that -5 is an eigenvalue and find its corresponding eigenvectors. So let's talk about how we would solve this. So for -5 would be an eigenvalue. A times x would need to be equal to -5 times x for some vector x that is not 0. So my eigenvector x is not allowed to be 0. Okay, so now what I'll do is I need to be able to figure out what x is. And what I'm going to do is I'm going to move everything over to one side. So I'll move the -5x to the left. So I'll get plus 5x equals the 0 vector. It's almost like an algebra problem in that I want to try to solve for this variable. And I see an x on both sides, so I'm going to try to move all the terms with an x to one side and then try to factor. So if I were to factor right now, like factor this x out of the left-hand side, I run into a problem. Because what I get is I get a plus 5 and then times the x that I've tried to factor out. And I get 0 on the other side. But is this true? Is this actually what I get here? It turns out that no. It turns out that this is not actually defined because A is a matrix, whereas the 5 is a scalar. And when I add two things, I need to add two things that are of the same type. Like I can add a matrix to a matrix, or I can add a scalar to a scalar, but I cannot add a matrix to a scalar. So I'm going to put a sad face. This is not something we can do. This is undefined. Undefined. We need to add things of the same type. So it doesn't make sense to add a matrix to a scalar. Okay, so I need another way to do this, to sort of get around this problem. So here's what I'm going to do. I need to somehow turn this 5 into like a matrix. So this is how we'll do that. I'll keep the first term as it is, ax. But what I'm going to do is I'm going to notice that the x is the same thing as having the identity times x. The identity, which is I, times x. Because the identity times any vector is just the vector x. So that's what I'm using here. And now 5i, this, if I think of this as a unit, this is a matrix. So now at this point I do have two things of the same type, and I can legally factor out. So what I'll get is a plus 5i times the vector x equals 0. Okay, so I need to figure out the vector x that sort of satisfies this equation. So let's compute the matrix a plus 5i at this point. So a plus 5i means, well, let's take the matrix A, which was 1, 4, 3, -3, and then add that to 5 times the identity matrix. So multiplying a matrix by a scalar means I multiply every single entry by that scalar. So 5 would multiply all the entries, which would give me 5, 0, 0, 5. And if I add these two matrices together, what will we get? We'll get a 6 here, we'll get a 2 here, and then the other entries stay the same, the 4 and the 3, because we're adding 0 to both of those. So we need to find a vector x that's going to be a solution to this homogeneous system. But how come with this matrix, how come when I look at the equation, like this homogeneous system, how do we know there's going to be a non-trivial solution? Because remember, x is not allowed to be 0. An eigenvector is not allowed to be 0. Well, it's the fact that this matrix has linearly dependent columns. They're actually multiples of each other. Linearly dependent columns. So because there's linearly dependent columns, so our equation that we're looking at, this equation right here, will have a non-trivial solution. And that's good, because we want x to be a non-zero thing. Okay, so let's go ahead and solve for x now. And when we do this, we will be finding the eigenvectors. Okay, so we need to row reduce our matrix. Let me just dive into the row reduction right away. So what I'll do is, I'm going to divide the first row by 2, or multiply it by a half. So 1/2 times row 1, and insert that into row 1. And that'll change the first row to 3, 2, while keeping the second row the same as 3, 2. And now I could subtract my 2 rows because they're the same. So I'll do row 2 minus row 1, and insert that into row 2. And that'll zero out the bottom row. So okay, 3, 2, 0, 0. Let me write that 2 a little bit better. And at this point, we can write down the equation for the first row. This is in echelon form. It's easy enough to solve from here. So we got 3x1 plus 2x2 equals 0. And if I isolate for the pivot variable for x1, I'll get x1 equals negative 2/3 x2. So now let's go ahead and write down our solution. So what could x be? So the first entry of x1 is negative 2/3 x2. That's what x1 was. And then x2 is free, so we leave that how it is. So x2, we keep it how it is. And now I can factor out my free variable and get x2 times the negative 2/3 times 1. Okay, so the solutions to this equation, the vectors x that work, look like this. x2 times this vector, negative 2/3 and 1. And what that means for our purposes is that any vector of this form, any vector of the form, x2 times negative 2/3, 1, with the condition that x2 is not 0. Because if x2 is 0, then this becomes a 0 vector, and the 0 vector is not allowed to be an eigenvector. So any vector of this form is an eigenvector for the eigenvalue lambda equals -5. Okay, so when we look at all the solutions to this system, so all the solutions have this form. So if we look at all the solutions, including the case where x2 equals 0, we have a term to refer to all of those solutions. And that's what's called the Eigen Space. And I want to state that definition next. Okay, so here is a more formal definition. The Eigen Space of a matrix A, corresponding to some eigenvalue lambda, is the null space of the matrix A minus lambda I, just like we computed in the previous example. Okay, so a couple of things I want to point out about this eigenspace. So the first is that the eigenspace will contain, this is going to contain, all the eigenvectors. All the eigenvectors for the eigenvalue lambda, and one other vector. The other vector that's in the null space is the 0 vector. Because remember, the 0 vector is not an eigenvector. So this eigenspace will have all the eigenvectors for lambda as well as the 0 vector. Okay. And we've seen before that the null space is an example of a subspace. So this eigenspace, because it is a null space of some matrix, it's going to be a subspace of something. This is going to be a subspace of Rn. So in our previous example, let's write out what the eigenspace was. So the eigenspace is all the solutions. Let me just say it's everything in the null space. So the way I would write that out is, I would say it's the span of the vector negative 2/3, 1. And where I'm getting that from is, remember, in the previous example, we said that the null space contained vectors of the form like our free variable times the vector negative 2/3, 1. In other words, it's anything that looks like this. But a more succinct way to describe this is to say, oh, this is just the span of this one vector. Okay. And then we could also talk about the basis for an eigenspace, just like when we talked about the basis for the null space. Well, the basis for the eigenspace is, it's the vector that sort of popped out when I wrote my null space in parametric vector form. It's just the vector negative 2/3, 1, without the free variable sort of attached to the front of it. So that vector on its own forms a basis for the eigenspace. But notice that these two things look really similar, like the eigenspace and the basis for the eigenspace look really similar. What's the key difference though? The key difference though is the eigenspace is the span of all the vectors that form a basis for it. So the key difference is the eigenspace has this word span in it, which means, oh, it's all linear combinations of those basis vectors that came from the parametric vector form when we found the null space. Okay, so I want to recap some of the key things that we've noted so far. So a number lambda is an eigenvalue. So I'm just going to abbreviate eigenval for eigenvalue. Lambda is an eigenvalue of A. If and only if, when does this happen? It happens when A times x equals lambda times x. When this equation has a non-trivial solution. That means there's got to be a solution where x is not 0. And what we noticed, how we rewrote this in our previous example, is we noticed that we could rewrite this in the form a minus lambda I times x equals the 0 vector by just rearranging the terms. So this is true if and only if this equation has a non-trivial solution. Okay, but now think of this whole thing, a minus lambda I, is just some matrix. And we're saying some matrix times x equals 0. This equation has a non-trivial solution. So that happens, a homogeneous system like this has a non-trivial solution if and only if this matrix has a linearly dependent column. So a minus lambda I has linearly dependent columns. Right, because when this homogeneous system has a non-trivial solution, that means our matrix definitely has a free variable. And that means that its columns are linearly dependent. And you guys might already have noticed that, oh, linearly dependent columns, that means our matrix is not invertible. But it's not the matrix A, it's the matrix A minus lambda I. A minus lambda I is not invertible, because that matrix has linearly dependent columns. Okay, and then finally what I want to end with is kind of a preview to the next section, 5.2, and relating this to determinants. So when a matrix is not invertible, that means its determinant, so in this case the determinant of a minus lambda I, is equal to 0. So this equation right here, this determinant being 0, we're going to see this in section 5.2. This is something called the characteristic equation. Don't worry about that name too much right now. We'll see it in the next section. But this equation will give us a method for how to actually find the eigenvalues if we're given the matrix. Because in this video, we haven't talked about that yet. We talked about how to check if something is an eigenvalue, but we didn't talk about actually how to find them if we're just given the matrix. And that's what we'll see in section 5.2. Okay, so let me just box that result